Previously, we covered the core foundations. Now, in part 4, we tackle Mars, interior and water history. Mars once had rivers. It may still have water today. So what happened in between, and why does it matter? In the last episode, we looked at Mars's surface, the craters, volcanoes, and canyons that define its landscape. Now we go deeper. This episode, the core question is this: what is happening inside Mars? What did its interior do to its water? And what does the answer mean for the search for life? That question isn't just academic. It's exactly what several active missions are trying to answer right now. Let's start with the basics, because they set the stage for everything else. Mars is the fourth planet from the Sun, sitting at an average distance of about 228 million kilometers. It takes roughly 687 Earth days to complete one orbit. A Martian day, called a sol, is just over 24 hours and 37 minutes, which is surprisingly close to our own. The planet is about half the diameter of Earth, and its surface gravity is roughly 38% of what you'd feel standing here. That lower gravity matters more than it might seem. We'll come back to that. The surface temperature swings wildly. From around 20 degrees Celsius near the equator on a summer afternoon, down to negative 140 degrees at the poles in winter. The atmosphere is thin, about 1% of Earth's pressure at sea level, and it's composed almost entirely of carbon dioxide, with traces of nitrogen and argon. There's no global magnetic field protecting it today. And that last fact is absolutely central to the story of Mars's water. Here's the open question I want you to hold on to. If Mars clearly had liquid water on its surface billions of years ago, where did it go? We'll get to that. But first, we need to understand what's going on inside the planet. In November of 2018, NASA's InSight lander touched down on the Elysium Planitia, a broad, flat plain near the Martian equator. Its primary instrument was a seismometer, a device sensitive enough to detect Mars quakes and, through those quakes, map the planet's internal structure. What it found was significant. Mars has a relatively large, low-density liquid core, estimated at around 1,800 kilometers in radius, made predominantly of iron with a surprisingly high proportion of lighter elements, including sulfur, oxygen, carbon, and hydrogen. Around that core is a silicate mantle, and above that, a crust that varies in thickness from about 24 kilometers under some lowland regions to roughly 70 kilometers under the ancient highlands. Crucially, the core appears to be liquid, but not convecting in a way that generates a magnetic field today. That's a very different situation from Earth, where a solid inner core surrounded by a churning liquid outer core produces a powerful planetary dynamo. And here's the thing: Mars did have a magnetic field. Ancient, heavily magnetized rocks in the southern highlands are a record of it. Scientists estimate that field shut down somewhere between 3.9 and 4 billion years ago. When it did, the consequences were severe. Without a magnetic field, Mars had no protection against the solar wind, a constant stream of charged particles flowing out from the sun. Over millions of years, that solar wind gradually stripped away the upper atmosphere. This is where the water story begins to break apart. Early Mars, in what geologists call the Noachian period, roughly 4 billion to 3.7 billion years ago, shows clear evidence of liquid water. There are valley networks carved by persistent flow, ancient lake basins, delta deposits, where rivers once met standing water, and minerals that only form in the presence of liquid water for extended periods. The Curiosity rover, working in Gale Crater, has spent over a decade characterizing sedimentary rocks laid down in an ancient lake that persisted for potentially millions of years. So the early planet was warmer, had a thicker atmosphere, and had water flowing on its surface. Then the magnetic field died, the atmosphere thinned, and surface water became unstable. But here's where it gets more complicated. Atmospheric loss alone doesn't account for everything. Some water was locked into the surface through chemical reactions with rock, a process called serpentinization, where water reacts with iron and magnesium-rich minerals. Some water migrated to the poles, frozen into the ice caps, and a significant portion was simply lost to space, broken apart by ultraviolet radiation into hydrogen and oxygen, with the lighter hydrogen escaping the planet's relatively weak gravitational hold. That lower gravity we mentioned earlier, it means Mars was always going to struggle to hold onto a light, energetic molecule like hydrogen. It wasn't just bad luck. The physics was working against Mars from the start. Now here's the open question I want to close. Where is the water today? The honest answer is that it's in several places, in different forms. The polar ice caps contain both water ice and carbon dioxide ice. Radar data from the Mars Express orbiter, and later from Mars Reconnaissance orbiter, suggests there may be liquid water, or at least a highly briny, possibly slushy layer, buried beneath the South Polar ice cap, though this remains contested. Some researchers argue the radar signal could be explained by other materials, and the debate is ongoing. Beneath the surface more broadly, there are strong theoretical reasons to expect permafrost, frozen groundwater, across much of the planet. Water ice has also been confirmed just beneath the surface at mid-latitudes, exposed by fresh impact craters and detected by orbital instruments. It's not a dry, dead world. The water hasn't vanished. It's changed state and location. What does all of this mean for geology? Mars is what planetary scientists call a one-plate planet. Unlike Earth, where the crust is broken into moving tectonic plates that recycle material back into the mantle, Mars has a single rigid lithosphere. Heat from the interior escapes differently, through volcanic hotspots rather than plate boundaries. The result is that features like Olympus Mons, the largest volcano in the solar system, at around 22 kilometers tall, grew to extraordinary size because the crust never moved away from the hotspot beneath it. On Earth, that same process creates island chains. On Mars, it built a mountain that dwarfs anything on our planet. But that same single-plate structure means less geological recycling, less outgassing over time, and a gradual slowing of the interior activity that once drove volcanic and hydrothermal systems. Hydrothermal systems are important because, on Earth, they're places where microbial life thrives in the absence of sunlight. If early Mars had active volcanic heat and liquid water simultaneously, and the evidence suggests it did, then the conditions for life were not obviously absent. That's the astrobiological thread running through all of this. It's not that Mars was definitely habitable. It's that the physical conditions, liquid water, chemical gradients, energy sources from volcanic and hydrothermal activity, and a reasonable supply of the right elements, were present for a long enough period that dismissing the possibility of life seems premature. InSight continued recording Marsquakes until its power supply failed in December of 2022, when dust accumulation on its solar panels became too great to overcome. In its 4 years of operation, it detected over 1,300 seismic events, giving us the first direct measurements of a planet's interior beyond Earth. The data is still being analyzed. There's more to learn from it. The picture that's emerging is of a planet that started with real geological vigor, a magnetic field, a thick atmosphere, liquid water, volcanic heat, and possibly the right conditions for life. And then, over billions of years, lost most of that to a combination of physics, chemistry, and the slow death of its interior dynamics. Mars didn't fail at being a habitable planet. It succeeded, at least for a while. The question is whether anything took advantage of it while the conditions lasted, and whether anything could have survived the transition to what Mars is today. Next time we look at Mars habitability. what the evidence actually says about the possibility of life, past or present, and what the missions looking for it are targeting. If you want to follow this whole series from the beginning, the full playlist is linked on the channel page. If you find this kind of careful, unhurried science useful, subscribing is the best way to keep up with new episodes as they come out. That is part 4 of Mars. In part 5, we explore the next key question. Subscribe so you do not miss it.